we are slowly ready to go on after our coffee break that we had in between the sessions quickly. We have Oliver and Cheng-Li here to basically talk about the new adaptive dictionary scan in HEX. And as I'm super curious, I think many others are as well. But with that, over to you guys to get us started.
Thank you, Thomas. Yeah, I'm a little bit excited to speak in this room and in this audience, to this audience. Thanks for welcoming us here at HANA TechCon. My name is Oliver Horn. I'm here with my colleague Cheng-Lun.
Hi.
We are developers in the HANA execution engine called HEX. And today we'd like to talk to you about a new feature, the adaptive dictionary scan, which makes our column store table search queries faster. First of all, I would like to tell you or explain why query optimization cannot stop at compile time and needs to continue at runtime. And then I introduce you to the column store data structures for those who don't know, and show you how the processing of a column store table search works in SAP HANA and especially the HANA execution engine HEX. I also explain the table scan and the two concepts of pre-filter and post-filter. And then I will hand over to my colleague Cheng-Lun, who will introduce you to the adaptive dictionary scan. So why does query optimization continue at runtime? The problem is real-world data is often not uniformly distributed, right? I have two examples here from the world of music. Musicians can choose freely between 24 musical keys, but yet some keys are dominating. So we have G major, C major, and D major, who are taking 30% of the market share of the songs, basically. And then there are some really disliked musical keys like this minor at the end of the scale. And in another example, we have the streaming count of songs. This is from a yearly year-end music report, and you can see that 99.8% of all songs in a streaming library are not streamed more than 1 million times. Only a tiny fraction of 0.2% of the songs is actually streamed more than 1 million times, and basically half of the share is only streamed maybe a few dozen times. So yeah, a really skewed distribution here in both cases. And now imagine you have a music catalog and you are searching for a song with a certain musical key and a certain streaming count larger than some threshold. So the questions, if you want to execute this query fast, what order would be best to evaluate the filter predicates here? If we evaluate the stream count first, it is good if the user enters an actual threshold larger than 1 million, because we only match 0.02% of the 0.2% of the catalog, and we have a small intermediate result. But if the user uses a 0 or any number less than 10, we match basically 50% or around that. If we go the other way around and start with the musical key, we don't know if the user uses maybe a G major, then we hit like 10%, or if he uses a this minor, then we only match some few percent. Then there are different costs of the dictionary evaluation. So this dictionary for the musical key is small. It just contains the 24 values, and scanning through it is basically cheap. But the dictionary for the stream count would probably be very large, like more than 100 million values, and it would be slow to scan through. Fortunately, our dictionaries are ordered, so we can do a binary search here, and this would be fast. But what if we add now another filter, for instance, on the artist name being like something, then depending on the actual pattern that the user uses here, we have either an expensive full dictionary scan for like an arbitrary pattern with wildcards in front and in the end, maybe even in the middle. And if it's just a prefix pattern, we can also do a binary search here. So prefix pattern means that the wildcards are only at the end. And we have a prefix. And another way to evaluate this would be if we have just the first two predicates evaluated, the musical key and the stream count, and they only match few rows, then it would be cheap to just evaluate the artist name on these few rows, basically. So as you can see, there are many different evaluation paths possible. And if we would compile a plan with a fixed order and evaluation strategy for these predicates for a parameterized query, it cannot be optimal for all cases. So we need flexibility in the query plan to adapt at runtime to the given query parameters. Now let me show you how the column store data structure looks like. Here only for main, you probably have heard that we have also a delta store, but it's pretty similar with some special implementations in the delta, but we are now focusing on main. So let's say this is our column with different artist names in it. Then all the distinct values go to the dictionary. And as you can see, the dictionary is ordered, and the position in the dictionary is what we call a value ID. So each distinct value gets this value ID. The value ID for the null is the size of the dictionary, but it's not stored here. And then we have the data vector, which contains for each row the value ID that sits in this row. You can also see that trailing nulls are not stored here. And additionally, if an index is created on the column, we have this index structure, which gives us for each value ID a list of the row positions that are matching the value IDs. For the null, there's no index structure. Okay, now how do we process a table search in HANA via HEX? We have three relational operators. The first one being the table scan, which is the most generic way for us to evaluate a column store table with or without a where clause. We also evaluate the visibility filter here. The table scan consists of three pipelines or steps to evaluate the different column store structures. In the first step, we evaluate the dictionary typically. In the second step, the index, if it's available. And in the third step, the data vector. Table scan produces a filtered result set, but it doesn't guarantee a specific order. So yeah, if the user wants a specific order, then you need to put an order by on top of it. Then we have a fast evaluation path for min, max, and top order by queries, leveraging an available index. And this one produces a sorted result set and applies the filter afterwards. And the third path is a unique index lookup, which is used for primary key lookups or other unique index accesses. Now we are focusing just on the table scan. And here we can decide for each filter predicate if we put it into a pre-filter or a post-filter. So what's the difference? A pre-filter is highly optimized and specialized for the column store. It uses pre-compiled code, but it is limited to certain predicates, mostly comparisons or the like predicate. It has various optimizations in it, like the binary search I already mentioned. We have the full dictionary scan, also an interval scan, and we can use the index. And we have some adaptiveness at runtime, means we can change the order of predicates that are put into the pre-filter, and we can, for instance, decide to do or skip the index lookup. In the post filter, however, we have this is a generic way to evaluate predicates. They are evaluated row by row. So for each row, we evaluate predicate by predicate by predicate, and then we know if the row matches or not. Then we go on to the next row. For the post filter, we use generated code. There's no adaptiveness at runtime. Everything is fixed at compile time. And this post filter is fast if we have a small intermediate result to work on. That's why we call it post filter, because we need an intermediate result that comes out of a pre-filter. So now, how do we go through the structures? For the pre-filter, we do this dictionary scan first. It gives us the value IDs for the matching, for the values matching the predicate. And then we go to the data vector, and we can scan it, find the row positions with the value IDs. And we do that in ranges of the table, so therefore we repeat it for each row position range. Then if we already have such intermediate result of row positions, we can also do lookups into the data vector and check if the value ID is on this row. Then we can decide if we keep or remove the row positions. And if there's an index, we can use the value IDs to look up the index, which gives us the row positions. And then we just need to chop the list of row positions to the current range that we are looking at. The post filter works kind of the other way around. We have this given intermediate result of row positions. Then we do the data vector lookup, which gives us directly the value ID. We go to the dictionary, do a dictionary lookup, which gives us the value, and then we can evaluate the predicate on this value, decide if the row position needs to be kept or removed from the result, and then we can repeat the process for the next row. So this pre-filter, post-filter decision is done during compile time, as I said. During compile time, we have limited information available. The actual parameters are unknown. We have something called a parameter-aware optimization, but it only optimizes for the first parameter set. So if during a later execution of the same cached plan, we have a different parameter set, it might have different intermediate result sizes, for instance. Also, the actual dictionary sizes and data vector sizes can change over time, so the plan might still be cached, but data is inserted into the table or deleted. And then the dictionary sizes, data vector sizes might look different during the next execution of the cached plan. Also, the actual result size from previous filters is only known at runtime. And as I said, the dictionary scan can be expensive if the dictionary is large. It can also be expensive depending on the actual parameters used in the filter. And for conjunctive filters, as I also said, we can leverage the small result from a previous filter and then run it, for instance, in a post filter. But the post filter, again, is not runtime adaptive, so it cannot be changed during runtime. Okay, and here comes in the adaptive dictionary scan, for which I hand over to my colleague Cheng-Lun.
Hi, so I'm going to introduce about the adaptive dictionary scan. So, but before that, let's define some terminology. So first is the late dictionary scan, early dictionary scan. So it's basically the dictionary scan that done as just described before, like the old days. And the late dictionary scan is we do a post-filter-like evaluation, and when the row position is already available. And then the adaptive dictionary scan is that the system will decide during the runtime whether I do early dictionary scan is better or late dictionary scan is better. And for this feature, we have a config dict scan mode. It can be set to early, adapted, or late. And currently, since QRC for 2025, the default is adaptive. And we also have a hint for the query that if you want to enable it or disable it for certain query, we also have a hint early dictionary scan, adaptive dictionary scan, and the late dictionary scan. Then, okay, so this is the early dictionary scan. So it's basically just the same as what we described before. And then the late dictionary scan. So the graph here looks very similar to the post filter that we just showed, and also the logic here. It also takes the intermediate result from previous filter, like the post filter dots. And then from this intermediate result, we do a row by row evaluation and decide if we want to keep this row or not. But this has some difference with the post filter. First, this late dictionary scan is part of the pre-filter. And also because the post filter is code generated, as mentioned before, this is not the post filter was not changeable at runtime. But for the pre-filter, we have some flexibility to change it. And also the adaptive dictionary scan reacts according to the runtime matrix, which might not be available during the compile time. So during the compile time, we might not choose the best or most optimal plan. But during the runtime, with the adaptive dictionary scan, we can adjust to according to the runtime matrix. For example, if we know the predicate, the like predicate is the metric pattern is the prefix pattern or the normal pattern. And also, the dictionary size is more accurate during the runtime because during the compile time and the runtime, there might be some more data inserted, so the dictionary size might already change. And also, during the runtime, we also got the result size estimation from the previous filter or even the result from the previous filter. So this is just a recap from the previous slide. So it's just showing you that basically the early dictionary scan looks like the pre-filter here, and the late dictionary scan looks like the post-filter here. But they have some differences, especially for the late dictionary scan and the post-filter. And then now let's take a look at some results. So with the previous example, we created a data set. So it's an artificial data set for this demo. And in this data set, we just have a very simple table, music catalog. And in this query, we try to select the string count larger than something. And the song, the name of the song, like something. And note that this is a parameterized query, so which means we don't know the parameter during the compile time, only at the runtime. And in this case, because this parameter is very selective in the first predicate, and yeah, so it might be better to do the post filter. So if you compare the early dictionary scan and the post filter, so before the adaptive dictionary scan, we can only decide either do an early dictionary scan, so like a pre-filter, or we put it into the post-filter. And you can see the compare results here. The CPU time of the post-filter seems better. Yeah, so in such case, if we have an adaptive dictionary scan, we will decide to do a late dictionary scan. Then it will evaluate or like the post-filter, so the performance is comparable with the post-filter. And this is the same query, but just a different parameter set. So in this parameter set, you can see it's actually better to do an early dictionary scan, so do it like a pre-filter. But if we put it into the post-filter, it will be, the performance might be not so good. And then, so you can compare also here the early dictionary scan and the late dictionary scan. If we have an adaptive dictionary scan, then we can decide to do the early dictionary scan here. So it's the performance is better than put it into the post filter. So yes, I think that's it all from our side. Yeah.
All right, perfect. So let me see if we have any questions from our audience on HEX. Maybe even wider questions on the topic, as we have two key experts here, and that is a rare chance for you to get hold of them, I guess. Seems like the audience is desperately looking forward to the lunch break, I feel. All right. So waiting the magically 3 seconds. If there are no questions, then thank you to both of you again for... Oh, there is one. Where is it? Ah, here. All right. Oop, my bad.
Yeah, thank you for the presentation. The question is just, you showed that it is available for HANA Cloud. Is this also downported somehow to HANA on-premise or HANA 2.0?
Yeah, we expect it to be included in HANA 2 SPO9.
Okay, thank you.